Okay, so we are going to do an example of the full problem-solving process with kinematics with a very basic one sort of object, one type of motion, one phase problem. And looking at that whole process, we've outlined that process to begin with. Now we're going to add in our equations and do the solving. So the problem reads, a boat is cruising at a constant velocity of 2.2 meters per second when it is shifted into neutral. After coasting 10 meters, the engine is engaged again, and the boat resumes cruising at the reduced speed of 1.6 meters per second. How long did it take for the boat to coast the 10 meters? How much time did it take for that boat to coast 10 meters? All right, so if we think about our process of problem solving, and that list you generated hopefully in the previous mini lecture, the first step is to define the object, conceptualize this big picture. So what is the object that we are analyzing the motion of? Well, that object is the boat. And now we need to define what the motion actually is. What begins the motion, what ends the motion, and then what type of motion are we dealing with? So our initial, what starts the motion, it says we're interested in how long it took to cruise that 10 meters when it was shifted into neutral. So our initial is when it shifts to neutral, and our final then is when it re-engages. All right, so what type of motion is this? Well, it's all happening in a single dimension, one plane, and we haven't quite got to that two dimension yet, but we will. And is it all happening with a single acceleration, or do I need to make this motion into phases? Well, it is only one acceleration, that time when it is in neutral, so it's a single phase problem. And there's only one object involved. We're only interested in the boat, so it's also a single object problem. As we start to conceptualize this, our problems will become more complicated. Okay, so the next step in the process is to define the world. We're going to set our origins, we're going to draw a picture, all that good stuff. So let's draw that picture. Here's our boat, and it's somewhere in the world when it shifts into neutral. Let's say that that is at position 0. That's at the origin. The origin is going to be when it shifts into neutral. And we're going to have the boat moving in the rightward direction, so positive direction. So here's our coordinate system, and here's our boat. All right, now it says that the boat has all these properties that we're going to look at. So after we set our coordinate system, define the world, we need to list our knowns, and those are our players. So we are going to have initial and final positions, initial and final velocities, the acceleration, and the time. Our initial position corresponds to the location when it shifts into neutral. Our final position corresponds to the location when it re-engages. Initial velocity, the velocity when it shifts into neutral. Final velocity, the velocity when it re-engages. The acceleration and the time, that time is this time that it's occurring, how long this process is taking, and of course the acceleration is during that time. So let's use the information in the problem to fill in our list. Initial position, well, I've defined that. I chose that to be the origin, so our initial position is at 0. It does say it re-engages after 10 meters, so at the end, we are at 10 meters. Our initial velocity, it says that the boat is cruising at a constant velocity of 2.2 meters per second when it engages into neutral. When it goes to neutral. When it re-engages the motor, it says it's traveling at a reduced speed of 1.6 meters per second. The acceleration is not given, but again, we want to be thinking about how might that look. Well, is there an acceleration? Is there a non-zero value for the acceleration? And the velocity is changing, so indeed the acceleration is going to be non-zero. We don't know what it is, but we know it's going to be non-zero. Now, can we make a prediction of whether it should be positive or negative? Well, we are moving to the right, and our value is going down. We're moving to the right, and we're slowing down. When an object is slowing down, the velocity and the acceleration need to be in opposite directions. And so if we're moving to the right, the acceleration should be to the left. It should be negative. So our prediction is that this is going to have a negative non-zero acceleration. The time, how long does it take for the boat to coast that 10 meters? That's not given. The time of this motion is not known. All right, our next step then is to identify what variable answers my question. Well, time answers my question. And so time is what I want to go after. Now, I have three equations that were given in the book, three really powerful relationships. I'm just going to write them up here for you to remind you what they are. We have a relationship that gives us information about an object's final position related to its velocity and its acceleration. We have a relationship that gives us information about an object's velocity that's related to its acceleration in time. And we have another relationship that, if I don't have time, that relates an object's final velocity to its acceleration and its change in position. So here are the three equations that your book gives you. These are the three equations that all we need to solve all of kinematics with constant acceleration. Now we want to know time. If we want to know time, we're going to want to use one of the equations with time in it. And it's always a good idea to pick the one that has most of the other stuff in it. Well, it turns out they both have all the other stuff in it except one. So let's just start with our velocity relationship. We have v final equals v initial plus acceleration times time. So if that's the equation I'm going to start with, v final, well, I'm given is 1.6. V initial is 2.2 plus, I don't know my acceleration and I don't know my time. So I need the acceleration in order to find the time. Well, if I go to this equation, well, I still don't know acceleration or time. So I need acceleration, and I need to do it in a way that's independent of the time. Well, that's where this equation is going to come in. So I need acceleration. I'm going to go after that acceleration. V final squared is equal to V initial squared plus 2a delta x. So it's always, remember, good to identify what you need, go after it, and then that'll tell you what you're going to need, and then go after it and follow that process until you can solve the equation. So V final is 1.6 squared is equal to V initial, which is 2.2 quantity squared, plus 2 times the acceleration times delta x, so 10 minus 0. All right, so we get our handy-dandy little calculators out. I'm going to use mine on my computer. We have 1.6 squared. So 1.6 times 1.6, and I kind of like to do the math out. This is a preference. You could rearrange everything and then plug in all the numbers at once if you want. 2.2 squared is 4.84 plus 20 times the acceleration. So I'm going to subtract 2.56 minus 4.84 gives me negative, that's a good thing, 2.28 is equal to 20 times the acceleration, and I find that my acceleration is equal to negative 1.14 meters per second squared. So now I can move that into this value. And it lets me utilize it to solve for my time. So I have 1.6 equals 2.2 plus negative 0.114, and that's good. It's consistent with what we thought it should be, times time. And so solving for my time, I have 1.6 minus 2.2, and then I'm going to divide that by a negative 114. And I see that my time is equal to 5.3 seconds. So it took that 5.3 seconds to travel those 10 meters. So what was our process? We have to identify the object. This is what you do anyway. You're showing in this process, you're showing your whole train of thought, your whole critical analysis of the problem. You define what the initial and final is of the motion. What is this time really that we're getting after? Identifying what type of motion it is in that regard will help facilitate our process. You identify the world because these values, especially these position values, are determined because of what you have set. They're not determined by anyone but you. And so you have to show how that has been defined, pulling the important information, making some assessment of what we expect things we don't know to be, so we can, one, evaluate it, but two, be critically thinking about the problem. Identifying what we need to answer the actual question. How long, how much time is a time need? Using our equations to go after that, picking one that has what we want in it. That'll tell us we don't have something. It tells us what we need. We then go after that, and we can solve our problem. Should the time be positive? Yep. If we had a negative value, we probably would have made a mistake, so we can evaluate that a little bit, and we can get any solution if we follow this process. Good job.